In exercise 3G, you're going to be learning a new algebraic technique that enables you to determine a function value as x approaches plus infinity or as x is approaching minus infinity. Now, that has very useful applications when it comes to sketching functions. If we know what our y values are doing as x is getting closer or approaching plus infinity, or in this direction as x is going to minus infinity, if we've got an idea of what our y values are at those ends, then it helps us to draw the graph. And apart from that, it's a very commonly examined technique. So really important that you understand the technique and then realise that once you understand it and can use it, that it has a practical application in terms of sketching graphs. Now you know that previously we looked at the function y equals 1 and x, that was your hyperbola. And in particular, we looked at as x got approached plus infinity. So as x is getting bigger and bigger, x being in the denominator, you know that your fraction is actually getting smaller and smaller, and we say the limit. We introduce this concept of a limit. As x approaches plus infinity, you're getting 0. Y is getting closer and closer to 0. And the limit as x approaches negative infinity was also 0. Now, that, as it says here, produces a very special limit. And this is something that you have to know, have to be able to recall and use. And that is, the limit as x approaches either plus or minus infinity of 1 on x is actually equal to 0. Now, what we're going to do is in our investigating the behaviour as x approaches plus and minus infinity, we're going to look at what this limit is. So, and then the limit will actually tell us the value of the function. It's the limiting value of the function. You can probably tell that the only time that we really get to use this concept is when x appears in a denominator of a function that we're either investigating or that we've been instructed to sketch. And the other thing that you also know about functions which involve an algebraic fraction is that they usually have a very easily identified vertical asymptote. So the values of x that create a 0 in the denominator of the function would be classified as a vertical asymptote. And what the limit as x approaches plus or minus infinity actually enables us, when we investigate that limit, that also identifies for us a horizontal asymptote. So as x is approaching plus or minus infinity of our function, then the limiting value is the value of the function that the y value of the function that it's getting closer and closer to, but it actually never gets there, which then means that that y value is a horizontal asymptote. And again, if you can identify horizontal asymptotes, then it makes sketching that much easier. Hopefully some of this, or all of this, will become clearer as we do an example. So it says here, if the function tends to a definite limit, as opposed to going off to infinity, which I guess if we found that as x approaches infinity, if our graph's going off to infinity, then it simply looks like that, which I wouldn't say is a definite limit. A definite limit is when we've got a value, a number, then we say, and if that number is b, for example, then we say as x is approaching plus or minus infinity, then the horizontal line y equals b is our horizontal asymptote. Now, this is a feature of sketches that you will do exclusively in extension 1. So you will be looking for functions that have horizontal asymptotes. How will you find the horizontal asymptote? You will investigate the limit as x approaches plus or minus infinity, and then you will also use this property that anywhere you get a 1 on x, you're able to replace it with a 0. So we'll actually be creating 1 on x in our function and replacing that then with zeros. How do we do that? We've got 2 very important steps. One, to find the limit, you must divide every term, top and bottom, of your function by the highest power of x in the denominator. And step 2, then you just use this special limit here. Like I said, as we work through some examples, it'll become more obvious what these steps actually are. So if you were asked to sketch, for example, this function, f of x is x minus 1 over x minus 4. Now, clearly, number 1, it's a function with x in the denominator. Now, there are 2 things we know from that. One is there will be a vertical asymptote, and we need to investigate whether there is a horizontal asymptote. So, first of all, let's establish, or at number 2 over here, let's establish that this graph and function does not exist when x is equal to 4. So x cannot be equal to 4, which means that in terms of our sketch at 4, we will have a vertical asymptote. Now, what the graph does on either side of that, we have to investigate. The best idea about what the graph is going to do is to look at x approaching plus or minus infinity to determine its behaviour there. So we want to know what the limit as x approaches plus or minus infinity of x minus 1 over x minus 4 would actually be. Now, remember step 1 above said to actually pursue this, we're going to use a special limit, which requires us to have some 1 on x's. To create that, we divide every term, top and bottom, by the highest power of x in the denominator. Now that's something worth just learning off by heart. So the highest power of x in the denominator is x, and so we're going to divide every term. So this is the limit as x approaches plus or minus infinity of x divided by x minus 1 divided by x all over x divided by x minus 4 divided by x. So that's going to give me, now we do some simplifying, the limit as x approaches plus or minus infinity of 1 minus 1 on x all over 1 minus 4 on x. And it's now at this stage, you can see, we've created some 1 on x's. We now actually use the special property. Use special property. What was that special property? It was that if you apply this limit, x is going to plus or minus infinity, then any 1 on x goes to 0. So, in my next step, I'm going to leave out this limit because I'm applying it. I'm actually now applying the limit. I'm saying that I know that as x approaches plus or minus infinity, this and this both go to 0. And so I'm left with 1 on 1, which is 1. So this graph is going to approach 1, a y value of 1. What can I immediately conclude? Therefore, y equals 1 is a horizontal asymptote. Yes, this graph does have a limit. It has a definite limit. And so we know that we will, for example, put 1 there, and we can include another dotted line indicating we've got another asymptote. You probably know enough about functions with x in the denominator to know that they're going to look like a hyperbola. And we've just established that as x goes to infinity, y is getting closer and closer to 1. And here, as x is going to negative infinity, y is trying to get closer and closer to 1. So we've got the tails of our graph doing that. The other thing we've got to investigate is what is happening as I approach 4 from the left-hand side, and what is happening to the y values as I approach 4. Oh, did I just say right when I meant left? Anyway, what is happening to our function values or our y values as I approach 4 from this side? So I'm talking about 3 and 3.9, 3.95, 3.96, etc., getting closer and closer to 4. And then on the other hand, I'm going to look at approaching 4 from the top side, so coming back. So let's have a look. So let's take, for example, when x is 3.9. So we're just here on this side of 4. We know what x is equal to 4, the graph doesn't exist. So putting x equal to 3.9 into our original function, we've got 3.9 minus 1 over 3.9 minus 4. The numerator is not that significant, 2.9. It's what's happening here in the denominator. 3.9 subtract 4 is a small negative number. Now, if we're going to divide by a small negative number, you know that dividing by a small number, it has the result of making the overall result very big. Positive divided by a negative, it's going to be a big negative number. Now, we could go even closer. We could go when x is equal to 3.99. And that way, think about what the denominator is doing. It's not so much the numerator, it's all focused on the denominator. At 3.99 minus 4, we would then be dividing by negative 0.01, an even smaller number you're dividing by, which results in a big number. Divide by something very small gives you a lot of them. Positive divided by a negative is a negative. You can probably work out then that the graph is going to head down here towards negative infinity. Likewise then on the other side, when x is equal to approaching 4, we get very small numbers, but they will be positive this time and the graph's going to go up there.